Good morning, everyone, and welcome back. Over the last several lectures, we have been building a toolkit. It's been quite a journey. We started with the fundamentals of pipe flow, understanding laminar and turbulent regimes. We derived exact solutions for laminar flow, giving us the Poisson's law and F is equal to 64 over Reynolds number relationship. Then we tackled the complex world of turbulent flow, learning about the Reynolds stresses and the viscous sublayer. And previous time we used dimensional analysis to bring order to that complexity, giving us the friction factor, the Moody chart, minor loss coefficients KL, and the hydraulic diameter for the non-circular ducts. We have spent all this time building the tools. Today, in this particular section, it is the moment of truth. Today, we finally get to use these. This is where fluid mechanics becomes engineering. This is where we answer the practical questions. How much pressure do I need to pump the water to the second floor? How big should this pipe be? How much flow will I get from this particular system? What happens when the pipes split and join together? So we are going to look at two main categories of the problems. Number one is the single pipes, and number two is the multiple pipe systems. Single pipe systems, we will be treating one continuous pipe, possibly with fittings, and the second one, multiple pipe systems, where pipes would be connected in series, parallel, or more complex networks. So let us start with the single pipes. Here we would be presenting a very useful way to categorize these problems as summarized in this particular table. There are three classical types, and the solution procedure depends heavily on which variable are given and which one you need to find. Type 1 is to determine the pressure drop or the head loss. This is the most straightforward type. In a type 1 problem, you are given the pipe, its diameter, length, and roughness, the fluid like its density, viscosity, and the desired flow rate. Your job is to find the pressure drop or the head loss required to drive that particular flow. Now, think of the example 8.8 in your textbook of Munson. You have a copper pipe running from the basement to the second floor. The flow rate you want out of the faucet 12 gallons per minute. The question is that what pressure does the water heater need to supply to make that happen? The procedure is direct. You know the volume flow rate, so you can easily calculate the velocity V. The diameter d and the fluid properties, so you can calculate the Reynolds number also. You know the pipe material, so from the table you can get easily the pipe roughness epsilon as we have discussed earlier in the previous lecture, and we can find the epsilon over diameter E by D ratio also. With Reynolds number and the epsilon over D, you can go to the Moody chart or use the Coolbrook formula to find the friction factor F. Then you add up all the minor loss coefficients from the table for the elbows, valves, and the faucet as we have discussed in the previous lecture. Finally, you plug everything into the energy equation, adding the major losses, which is the FL over dV square over 2G, and the minor losses, which is the sigma KLV square over 2G, and solve for the pressure at the inlet. So it's a straightforward calculation. You know the flow, you find the friction factor F, you compute the losses. So type 1 is like following a recipe. As long as you have the ingredients, the answer comes out cleanly and easily. Now we come towards the type number 2, which is to determine the flow rate. So type 2 problems are where things get more interesting. In this case, you are given the pipe and the fluid, and you are given the driving pressure or the head loss that is available, but you don't know the flow rate. You need to find the volume flow rate Q. Now, example 8.10 of the Munson book is closely related to the this type of problem, where a fan provides a fixed amount of the head to move the air through a ventilation system. The question is, after remodeling with a longer duct and more fittings, will the flow rate still be within the safe range of 6 to 12 cubic feet per second? So here is the challenge to find the head loss. You need the velocity V. To find the friction factor F, you need the Reynolds number, which depends upon the velocity V, but V is what you are trying to find. Velocity is what you are trying to find it in this particular numerical. So you have a clear dependency. F depends upon and V depends upon the friction factor F. So this requires a trial and error iterative solution. The procedure goes on like this, that you make an initial guess for the friction vector F. A good starting point is often around zero point 0.02 or zero point 0.03, or you can guess a value from the fully rough portion of the Moody chart for your relative roughness. Second step is that with the guessed value of the F in the step number 1, you solve the energy equation for the velocity V. Now with this calculation in step number 3, with the calculated value of the velocity from step number 2, you compute the Reynolds number value. In the step number 4, with this new Reynolds number and your known value of E by D, you go to the Moody chart and look up a new improved value of F. And subsequently in step number 5, you compare this new value of F friction factor with your initial guess. If they are close enough, you are done. If not, you use the new value of f as your next guess and repeats the step number 2 through 5 until the value of the f stops changing. So this is called iterating to convergence. In example 8.10 also, they start with the guess of friction factor equals 2.019. Calculate the velocity, get a new value of f of 0.022, and then iterate again until it stabilizes. So this is a fundamental skill for any engineer. You will do this often. Now, next type of the problems is type number 3, which is to determine the pipe diameter. Type 3 problems are the most challenging one. In this case, you are given the desired flow rate and the allowable pressure drop, and you need to find the pipe diameter that will make this work. So this is the design problem. Think of the example 8.12 as listed over here. So you need to move 2 cubic feet per second of air with a pressure drop no more than zero point 0.5 psi per 100 feet of pipe. So what diameter pipe should you specify? The difficulty here is that the diameter D appears everywhere. It's in the velocity, V is equal to Q over A, so V depends upon the diameter raised to the power 2. It is in the Reynolds number also, so Reynolds number depends upon the velocity and diameter. It's in the E by D ratio also, and it's in the head loss equation itself. So you have one equation, but F depends upon D in a complex way. So this also requires an iterative approach. The procedure is similar to the type 2 problems which we have already discussed, but now you are iterating on the diameter D. Here we would be iterating for the diameter D in the 5 simple steps. First of all, in step number 1, you guess a value of the friction factor F. Likewise in the type 2 problems. The step number 2 is using the energy equation, you solve for the diameter D based on that guessed value of F. Step number 3 is that with this diameter D, you calculate the velocity V and then the Reynolds number and then E by D ratio. In step number 4, with Reynolds number and E by D, you go to the Moody chart and find a new F. And finally, in step number 5, compare. If they don't match, adjust your guess and repeat the process. In example 8.13, it adds another layer of complexity by including the minor losses. This makes the equation for D even more complicated. So the text suggests that in this case, it might be easier to guess a D diameter value first, calculating the corresponding F from the energy equation, and then check that the friction factor against the Moody chart. This is different iterative path, but the principle is the same. You keep adjusting your guess until all the equations are satisfied. Now, the conceptual framework for the single pipes, before we move on, let us step back and see the big picture. These three problem types cover almost everything you will encounter with a single pipe. Type 1 problem is analysis. You know what you are putting in the flow, you find out what you need, like the pressure, and In the type 2 problems is the performance prediction. What you have available pressure, you find out what you will get flow. Type 3 is the design in which you know that what you want, flow and pressure, you find out what to build like the diameter. So the key takeaway is that the energy equation is always your starting point. It connects the pressure, elevation, velocity, and the head losses. The head losses themselves are expressed using the friction factor and the loss coefficient KL, which we spent so much time understanding in the previous lecture also. So when friction factor is unknown because it depends on the answer, you must be prepared to iterate. So this iterative process is not a failure of analysis. It's a recognition of the real world. It's what engineers do. And with modern computers and calculators, it is much faster than it used to be. But the conceptual understanding of why you are iterating is still essential. Then we move on to the next topic, which is the multiple pipe systems. Now, let us take it up a level. What happens when you have more than one pipe? What if the pipe splits or merges or take different paths? So in this section, we will be discussing about the multiple pipe systems. These systems are everywhere. The complex system of the tubes in your lungs, branching from the trachea down to thousands of tiny bronchioles. City water distribution networks are another classical example. The physics is the same, but the complexity increases because we have multiple unknowns. So we will be going through several common configurations. Number one is the pipes in the series configuration. So look at this particular figure. This is the simplest multiple pipe system. Pipes are connected end to end. In this case, every single fluid particle must pass through every pipe. So the governing principle is the flow rate is the same in each pipe, which we can write it as Q1 must be equal to Q2 must be equal to Q3. But the head loss from the beginning to the end is the sum of the head losses in each individual pipe, which we can write it as HL total equals to the summation of HL1 plus HL2 and HL3. So if you are given the flow rate, this is a type 1 problem for each pipe added together, a straightforward one. But if you are given the total head loss and need to find the flow rate, it becomes a more complex iteration because each pipe has its own friction factor that depends on the common flow rate Q value. Now the second scenario is the pipes in the parallel configuration. Now look at this particular figure. The flow splits at the point A and rejoins at the point B. A fluid particle can take any of the paths. The governing principles are different. First, conservation of the mass tells us that the total flow rate into the junction must equal the sum of the flow rates in each branch, which accounts for the following equation as Q total must be equal to the sum of the individual flow rates as Q1 plus Q2 plus Q3. Second, and this is the key insight, if you write the energy equation from point A to point B for a particle traveling through any of the branches, you will find that the head loss from A to B must be the same regardless of the path taken. Why is this so? Because all the particles start at the same pressure and elevation at point A, and it ends at the same pressure and elevation at the point B. So we can write it as HL1 equals to HL2 equals to HL3 equals to HL from A to B. So this is a powerful constraint. It means that even though the pipes may have different diameters, lengths, or roughnesses, the energy dissipated per unit weight of the fluid traveling through any branch is identical. Solving parallel pipe problems often involves expressing the head loss in each branch as we have already seen earlier, HL equals to FL over dV square over 2G, and then using the fact that these head losses are equal to relate the velocities in each pipe. So you then combine this with the total flow rate equations to solve the individual flows. Now we move on to the another type of the configuration, which is the three reservoir problem as displayed in this particular figure and example problem. So this is a classic, more complex problem. Three reservoirs at different elevations are connected by three pipes that meet at a common junction. The challenge here is that you don't even know which direction the flow is going when the flow is going in the pipe connected to the middle reservoir B. Is water flowing into the reservoir B, or is it flowing out of it? So you don't know. It depends upon the elevation of the junction point, which is not given directly over here but is determined by the flow. The solution procedure requires an assumption. As shown in this particular example, you start by assuming the flow direction in the pipe 2. Let us say you assume the flow is out of the reservoir B towards the junction. Then you write the energy equation from the reservoir A to the junction and from the reservoir B to the junction. Then give you two expressions for the pressure at the junction, and for consistency, these pressures must be equal. This gives you an equation relating the velocities v1 and v2. So next you write the energy equation from the junction to the reservoir C. This gives you another equation relating the velocity v3. Finally, conservation of mass at the junction gives you v1 plus v2 must be equal to v3 if both are flowing towards the point C. So you now have three equations for the three unknown velocities. You solve them and you get numerical values. But here is a crucial check. Does your answer make sense with your initial assumption? If your assumed flow is out of the reservoir B, then your calculated V2 should be positive in the direction you assumed. This is the important check. So if it comes out negative, that means your assumption was wrong and the flow is actually into the reservoir B. You then have to resolve the problem with the correct flow direction, with which is the sign in the mass balance and the energy equations. So this is the beautiful example of engineering judgment. You don't just crunch the numbers blindly, but you make a reasonable assumption, do the math, and then check the physical plausibility of your result. So if it does not make sense, you revise and try again. So let us bring this all together. Today we put our entire toolkit to work. For single pipes, we learned to categorize the problems into three types. Type 1 is to find out the delta P given Q is a direct approach. Type 2 problems where we have to find out the Q and we were given the delta P. While type 3 problems, we were to find the diameter D given the volume flow rate and the pressure drop. So it would require the trial and error iterations because the friction factor depends on the unknown answer. Secondly, for the multiple pipe systems, we learned that the same energy and mass conservation principles apply, but we have to account for the interconnections. In series, the flow is constant, head losses add. In parallel configuration, the head loss is constant across the branches, flow rates add. In more complex systems, like the three reservoir systems, we may need to assume the flow direction and then verify our assumptions. So the key message for today is this, that you now have the fundamental tools to analyze almost any pipe flow problem you will encounter. So the procedures are logical. Start with the energy equation, express losses in terms of the friction factor F and the KL, minor loss coefficient KL. So use the Moody chart or Coolbrook formula to find out the friction factor F, and if necessary, iterate until you find a consistent solution. So next time we will look at how we measure the flow rate in the pipes using devices like orifice meters and venturi meters, and we will see how our understanding of losses apply to those as well. So for now, practice recognizing type of the problem you are facing. Is it type 1, type 2, or type 3? Are the pipes in series or parallel configurations? So once you know what kind of problem it is, the path forward becomes much cleaner clearer. Thank you. See you next time.